So this is about basic concepts in differential equations. The first part of differential equation is a bit boring because it is more on terminologies, no? Definition of terms. So we're going to begin with the following physical phenomenon in radioactive substance. No? So basic concepts in differential equations. So let me begin by considering the following phenomenon. So consider the decay of a radioactive substance. This decay of radioactive substance can be described by the equation derivative of R represented by capital R, our amount of radioactive substance. So the derivative of R with respect to T, and that is equal to negative KR. Where here, K here is a constant. Notice the quantity derivative of R with respect to T involved. This is the instantaneous rate of change of the amount of radioactive substance. So again, this quantity means instantaneous rate of change of the amount of substance, our substance, radioactive substance. Do you still remember in your chemistry those that are radioactive substances, guys? Like for instance, I think titanium, radium, present at any time t. Okay? Or simply, mathematically, it means derivative of R with respect to t. Still remember, guys? In your calculus, this means derivative of R, our R represents the amount of radioactive substance. Derivative of R with respect to T. Okay, guys? So that's what we mean by derivative of R with respect to T. Physical interpretation, rate of change of the amount of radioactive substance present at any time T. So again, those radioactive substances that you had in your chemistry, perhaps you encountered or you heard them, radium, titanium, plutonium. So these are just some, no? We call this equation, derivative of R with respect to T equals negative KR, a differential equation. Okay, so by now, you know at least what a differential equation is based on this example, right, guys? So what do you notice? What is the difference between a differential equation and the equation that you had in your algebra, guys? It's also an equation like what you had in your algebra, but what do you notice? What's the difference? What do you think? It involves what? It involves a derivative. Okay, guys? Guys, Do you hear
Yes,
me?
sir.
So,
Yes,
So
po.
that's the difference. So from here, we can now define what a differential equation is. But of course, there are so many physical situations described by what? Described by a differential equation similar to this. This is not the only one. This is just one case. Okay? Is that clear, guys?
yes po.
Yes, sir.
Okay. So, what is a differential equation? So when you say differential equation, it is an equation that involves what, guys?
Ano contains functions po.
So it is an equation that involves
One
One
or
or
more functions and
functions.
their derivatives po.
one or more
Functions.
Functions.
derivatives, no? One or more derivatives. And when you talk of derivatives, it involve
Rate of
functions, no?
change.
So derivatives of functions. And of course, when you differentiate relative to what? One or more independent variables, no? With respect to one or more independent variables. So this is what we mean by differential equation. And many books just define differential equation as an equation involving what derivatives, as simple as that. So it is implied already that when you have derivatives, possible, of course, to have derivatives of one or more functions, no? And that is with respect also to one or more independent variables. Okay, guys? Is that clear, guys?
Yes.
Yes
Okay,
po, sir.
so
Opo.
in every differential equation, it contains a dependent and independent variable. Okay? Since derivatives are involved in a differential equation, it means that it has either explicitly or implicitly at least one dependent variable and at least one independent variable. In a differential equation, the dependent variable is called what?
Y po.
Is called the variable whose derivative is what? Is taken. Okay? So for instance, so let's say I have this equation. Derivative of r with respect to t from what we had in the beginning equals negative kr. Okay? Where k here is what? K is constant. Okay? So what are the variables here? We have r and t. Am I right, guys?
Yes po.
Opo, sir.
Okay, so in this equation, R is the dependent variable. So again, dependent variable here, R. What about the independent variable, guys? So independent variable is small t, no? And the big R is the dependent variable. So when we say dependent variable, relative to the concept of differential equation, it means that it is the variable whose derivative is taken. Again, it is the variable whose derivative is what? Is taken. Okay? Is that clear, guys?
Yes po.
Like for instance, if you have y equals x squared, if you take the derivative of y, so that is our considered dependent variable. What about independent variable? Guys, anyone? Guys, it is the variable, a derivative is taken with respect to. Okay? So again, it is the variable a derivative is taken with respect to. Okay? So in this case, in our example, what is the independent variable again? T. So it means we take the derivative of r with respect to that. Is that clear, guys?
Yes po.
Okay,
Yes
so
po, sir.
let us have some more of these differential equations, okay? So let's say we're given the following. We have differential equations, and then dependent variables, independent variables. Okay? Number one, if my differential equation is, for instance, we have y triple prime. This is one notation for derivative, no? We call this prime notation. Quantity squared, so third derivative, that is y triple prime. Quantity squared plus xy double prime. And this is, let's say, equal to kx y prime. So given this differential equation, what do you think is the dependent variable here? Since we take the derivative of y, so it means the dependent variable is what? Is y, right? Am I correct, guys?
Yes po.
Now,
Yes po,
if
sir.
it is not implied, I mean, if it is not explicitly written, understood that the independent variable here is x. If there, although there is x already here, so we are really sure that the independent is x. But in case, let's say there is no x here, it is implied that the independent is x. Okay? It's not explicitly expressed in the given equation, but if there is no other variable, so we are going to consider that with respect to that variable. I mean to x. Is that clear, guys? And what is the role of k here? K here is just a constant. Am I clear with that?
Yes po.
What
Yes
about
po.
the second
Yes, sir.
one? Let's say we have derivative of s with respect to p, and that is equal to, we call this Leibniz notation for derivative. So what is nice in the Leibniz notation is that the independent and dependent are clearly expressed, especially independent, no? It is written, unlike in the prime notation. So, and that is equal to, let's say, 4/3 RP let's say RQ. RQ multiplied by Q times the derivative of R with respect to P plus R derivative of Q with respect to P. What about this? So we differentiate how many variables, guys?
1.
So just one. What about derivative of R? Derivative of Q? So there are 3, no? So it means there are 3 dependent variables, okay? S, what else? R,
R.
and then
And
Q, no?
P.
Yeah. Arrangement does not matter as long as you have list all of them, okay? And what about the independent variable?
Yung people.
Just
P.
the P, no? Because these variables are differentiated with respect to that letter. So the only independent variable here is the P. Okay, guys?
Yes.
Next, what about
Yes,
number
sir.
3? What if I have second derivative, partial derivative of beta with respect to, let's say, with respect to big T, then with respect to big P. And this is equal to negative K times second partial derivative of kappa twice with respect to big T, and then plus second partial derivative of, again, same kappa. This is kappa, not the K, no? Kappa with respect to big P, twice with respect to big P. Second partial derivatives are involved here. So it means this is a what? Actually, once we study classification of differential equations in particular types of differential equations, the first 2 are ordinary differential equations. These 3, third one is a partial differential equation because it involves partial derivatives. Okay? So we partial differentiate what variables, guys? Beta and
T.
kappa, right?
Beta and kappa.
Then what about independent variables?
P pati T.
So remember, if you have partial derivatives, expect that there are more than one what? So more than one independent variables, no? So what are they? P and
T.
T, no? So P and big T, no? And big P and big T. Okay? So K here is constant. It's just constant. Let's have number 4. What about this number 4? We have U with double subscript X and then plus U double subscript Y is equal to 0. Now, in differential calculus, you learn that partial derivatives are also what? Expressed in terms of subscripted notation, can be expressed also in this form, no? Remember that, guys? These are partial derivatives in subscripted notation. Okay, so how do we read this? Second partial derivative of U twice with respect to X, or simply with respect to X because there is no confusion. Huh? And then second partial derivative of U with respect to Y, or twice with respect to Y if you want. Okay, guys? So
Yes po.
what is the dependent variable here? U, no? And independent is what? X.
X and Y.
There are two, no? X and Y. The independent variables are X and Y. Okay? Let's have the last one. Number 5. We have derivative of B with respect to T. I am differentiating actually with respect to R. Then 2R squared plus 3R minus 1. So this is what? This is in fly-spec notation. We call this in fly-spec notation. In fly-spec. The reason why it is fly-spec, spec means a little thing that very tiny that gets into your eye, no? Spec. Okay? So fly-spec, fly because it's hanging above a letter. So fly-spec. Okay? So what is not nice in this notation is that similar to derivative y prime notation, it does not clearly what? Express or gives. It does not clearly express or give the independent variable. You have to look at the what? The other letters or letter involved. In case there is no other letter involved, of course, it will be told to you what the independent variable really is, or it will be clear in context. Perhaps you know the situation, no? So that you will know what the independent variable is, even it is not written. Okay, guys? Like for instance, if I have B with that on top is equal to 4, you do not know anymore what the independent variable here is, but it will be told to you. You do not have to worry. Or it will be clear in context. Okay, guys? So here, what is the dependent variable? V, no? And then, what about the dependent, guys?
R.
Independent.
R po.
R. Okay, good. Because that is the only letter, another letter involved, no? So we assume that it is with that letter, with respect to that letter. Unless otherwise stated not, no? Okay? Am I clear with this now, guys?
Yes po.
Yes po.
Okay. Differential equations can also be expressed, guys, in terms of sorry, in terms of differential, no? Like for instance, the following. So again, differential equations in differential form. So meaning, not involving derivatives, but differentials. Like for instance, we have x squared plus y squared quantity multiplied to dx, and then plus 2xy dy is equal to 0. So this is a differential equation in differential form. What is not nice here is that it does not clearly define what the dependent and independent variables. Okay? So it depends on the situation, or if it is written like this, you have the option. So possible that x is the dependent, possible that y is the dependent. If x is your dependent, independent is y. If your y is dependent, the independent is x. Okay, guys? So there are two possibilities here if it is written this way. Unless your teacher agrees with you that every time you have x and y, the dependent is y. Okay, guys? But why is that always the case that it is the dependent? Possible also that x is the dependent. Clear, guys? Okay, number 2, we have r cosine theta dr minus r squared plus 1 quantity d theta. Okay? Is equal to 0. So the differentials involved here, dr and d theta. So possible, R is our dependent. Possible also that theta is dependent. But in analytic geometry, a form like this, involving R and theta in your analytic geometry, normally R is the dependent and theta is the independent. Remember, we have R as a function of theta, polar form, no? But if you are not told that R is the dependent and theta is the independent, then it is possible that theta is what? Is the dependent also. Okay, guys? And if that is the case, R is the independent. What about if we have this? Derivative of V is equal to 2 pi R H dr plus pi R squared dH. Okay? Yeah. So this, I think, comes from what function, guys? What do you think, guys? Volume of what? Function. What function? Function B, which is in terms of pi R squared H, no? Volume of what? Guys. Let me, I want it, because in, you know, in cylinder, R is not varying, no? So if this will represent volume of, for instance, of cylindrical shape or container, so you, in a cylindrical container, the radius does not change, right? Am I correct, guys?
Yes po.
Oh, so this actually does not represent that, no? So for this to represent really a volume of a container, let us have what container? Let me have it for a cone, no? So that R is varying also. Am I correct? Because in a cylinder, radius is not varying, only the height. No? Am I correct? If let's say you put water, as the water level increases, what is happening to the radius? It still remains constant, no? And only the one that is varying inside between the R and the H, just the H, and of course the volume. Okay? What's the differential of this? Derivative of B, that is equal to 1/3. There is pi, no? Yan. 1/3 pi, then the first differential of the second plus the second differential of the first. So you have 2R d what? dr, no? Am I right, guys? That's it. So this is in differential form. Okay? Is it clear now, guys? Guys. Okay? So these are differential equations in differential form. Differential equations are classified in different ways. There are many classifications, no? So we have classifications of differential equations. Depending on the distinctive features the equation contains, no? Yan. So classification of differential equations. By the way, we normally abbreviate differential equation DE, no? Differential equations, we just put S. Okay, guys? So what are the different ways of classifying differential equations? So there are many, and we will be focusing only on 4. But it doesn't mean, for the meantime, but it doesn't mean that differential equations are classified in just these 4 classifications, okay? So more than this, no? But for the meantime, we will be focusing in the following classifications. Classification by type, by order, by degree, and then by linearity. Okay? Clear now, guys? So these are not the only classifications. Huh? There are still many. And our focus will just be for these four for the meantime. So let's start with the first classification, classification by type. So what do we mean by type of a differential equation, guys? So we look at what? By type of differential equation, we look at the type of derivative involved in the differential equation, whether ordinary or partial. So that what we mean by types of differential equations. So again, we look at what? We look at the type of derivative involved, whether ordinary or partial. Hence, we have two types of differential equations. Number one, we have ordinary differential equations. Which we are going to abbreviate ODE. Okay, guys? ODE. So what do we mean by this differential equation? So ordinary differential equation is a differential equation that involves ordinary derivatives of functions of a single variable. Okay, guys? So again, one that involves only ordinary derivatives. No other derivative type. Okay? So just ordinary derivatives of what? Of functions of one variable. Okay? Is that clear, guys?
Yes po.
So like what we had in our examples, no? If you have one dependent variable, you have what? You have only one independent, pag ordinary. But the dependent can be more than one, as long as the independent, just one. Is that clear? You can have two dependent variables, but to be differentiated relative to a single variable. Okay, you can have three dependent variables to be differentiated relative to just one the independent variable. Okay? So examples, we have the following. Number one, derivative of y with respect to x is equal to cosine of x minus sine y. No? So this is an example of an ordinary differential equation. Why is it an ordinary differential equation, guys? Anyone? Guys? Because what? The derivative involved is just ordinary. Okay? So this is ordinary derivative. Am I clear with that, guys?
Yes po.
If you're asked of the dependent, what is the dependent here? Y, no?
Y po.
Independent is x. Okay? What about this one? This is also an ordinary differential equation in fly-spec notation. There are three dots. Actually, when you use fly-spec notation, you are allowed to have maximum of three dots only, meaning you are allowed to have this notation for up to third derivative only, because it's not easy to what? To count the number of dots if more than, no? Understood that if there are so many, maximum of three. So if you have just possible to just have two second derivative and then one for first derivative, na? So minus 5 second derivative of S, and then quantity cube equals 4t squared minus t cubed plus 4. Okay? So this is also an ordinary differential equation because just involving what? Ordinary derivatives. Okay? Third derivative and second derivative. Okay? Number 3, we have derivative of C sub B. This is actually in chemical engineering, I think. Derivative with respect to C sub A, and that is equal to -1 plus K sub 2 over K sub 1. So understood that this is K sub 1, K sub 2 is a constant, no? Over K sub 1. K sub 1 is also a constant. And then multiplied by C sub B over C sub A. Okay? I think this is about chemical reaction, if I'm not mistaken. Okay, guys? We have number 4, derivative, third derivative, minus 8 or capital D cube minus 8 applied to y is equal to 4x plus e to the x yan. Okay? Now, we will have this during the final period. We call this the denotation, which is red d cube minus 8 applied to y equals 4x plus e to the x. This is the denotation. Denotation for derivative. Capital D. Remember, if I have D applied to y or capital D applied to y means derivative of y. Okay? Denotation. Capital D. For derivative, no? And that is actually the same with this notation. Derivative, third derivative of y minus 8y. That is what it means. This left side. Okay? Clear now, guys? So these are just, of course, some of those ordinary differential equations. Let us have the last one. Number 5. We have, of course, this equation x minus y plus 1 quantity dx, then plus 2xy plus y quantity dy equals 0, which is in differential form. Okay? So if you divide this by dy, you will have ordinary derivative with dependent variable x. If you divide this by dx, you have what? Involving derivative of y with respect to x, having y as the dependent. Okay? So there are two possibilities here. Either you write it what in the form x minus y plus 1 quantity dx multiplied by dx over dy, okay, plus 2x plus y. Or you can have it x plus negative y plus 1. Then we have what, guys? Guys, still alive, guys?
Yes po.
2x plus y, then derivative of y with respect to x. Okay, equal to 0. This also equals 0. Okay, guys? So if you have this form, the dependent is x. If you have the second form, the dependent is y. So there are two cases. Unless your teacher, for instance, told you that the dependent is y, therefore you have just this one. Okay? And these are just some of those examples of ordinary differential equations. The second one, guys, we have number 2. Partial differential equation. Or anyone? What is a partial differential equation, guys? Or PDE? Any idea, guys?
It contains multiple variables po.
This contains also multiple variables, x and y, and even this equation. This involves multiple variables, but this is considered ordinary differential equation. Guys, what is a partial differential equation? One involving what? Guys, one that involves
More than one independent variable po.
more than one what?
Independent variable po.
Yes, no? So one that involves partial derivatives. If you have more than one independent variable, meaning 2 or more, when you take the derivative, it will involve partial derivatives, no? One that involves partial derivatives. And if you have partial derivatives, automatic, more than one, your independent variable. Okay, guys? Yan. One that involves partial derivatives of what? Of functions of several variables, no? And of several variables. Okay? With respect to what? So meaning with respect to more than one variable, no? If you have functions of several variables, with respect to what? With respect to more than one variable. So meaning more than one variable, more than one independent. More than one independent. Yan. Okay? Clear, guys?
Yes po.
So examples, we have partial derivative of f, second partial derivative of f with respect to x, or twice with respect to x if you want to be specific. But if it's just one type of independent below, you can just read it second partial derivative of f with respect to x, or to be specific, twice with respect to x. And that is equal to, let's say, second partial derivative of f with respect to y, then with respect to x. Look at how I read this, ha? Second partial derivative of f with respect to y, then with respect to x, plus 2xy, first partial derivative of f with respect to x. Okay? Clear, guys? So, if you write this in subscripted notation, this means f, then with double subscript xx, no? What about this one? F, y, x. Look at how the arrangement is written if it is in subscripted. Second partial derivative of f with respect to y, then with respect to x. In the del notation, so to the right, you have the y, and to the left, you have the x, okay? And then what about this? This is f with subscript what? X. Okay, guys? Am I clear with this, guys? Okay? So,
Yes.
second one, you have, let's say, u with triple subscript x, meaning third partial derivative, thrice with respect to x, minus u with double subscript y, and that is equal to u then with the following subscript, theta xy. Okay, guys? So this is another partial derivative, no? I mean partial differential equation, because this involves what? Partial derivatives. Okay? So in del notation, how do we write this? Third partial derivative of u, yan, with respect to x. Look at how I write x with superscript 3. It doesn't mean it is exponent. What about the second one? This means what? Second partial derivative of u, yan, with respect to y. And then the last one, this one, third partial derivative of u with respect to y, with respect to theta first, then with respect to x, then the last one with respect to y. Am I right, guys? Am I clear with this? Guys?
Yes,
Yes
po.
po.
Okay, so look at how the notations for subscripted and del notations are written, huh? So
Sir,
the arrangement, look at how
ko lang.
this is interpreted.
Sir, can you
Yes.
interpret po ulit sa yung pangatlo pong arrow?
Yes, this one. If you
paano
begin
po?
with theta in the subscripted, that is the extreme right in the del notation here at the bottom.
How can you say it, sir?
Third partial derivative of u with respect to theta, then with respect to x, then with respect to y.
Okay po.
Okay?
Yes po.
You had this when you were in differential calculus. Okay? And next, number 3. You have to be careful the way it is read, huh? Then we have, let's say, partial derivative of big T with respect to small t. So they are different variables, and that is equal to, let's say, alpha. Then multiply to second partial derivative of big T with respect to what? With respect to, let's say, x, or in particular, twice with respect to x. So another partial derivative. Okay? Number 4, we can have, let's say, square root of second partial derivative of v with respect to x, meaning twice with respect to x, and that is equal to, let's say, a squared, then third partial derivative of u with respect to z, then twice with respect to x. Okay? Plus partial derivative of v with respect to z. Okay, guys? Yan. Another partial derivative. And this is partial derivative also. Therefore, this is a partial differential equation. Any question with this, guys? How many dependent variables do we have here? Guys, Americans pronounce it variable. What do you want? Variable or variable?
Variable.
You want variable? You do not want to be an American? I'm not really sure for British, no? So, yeah. How many dependent variables do we have? If you're asked, guys, there are two.
Two.
What are they?
V and U.
V and U. Okay? Not me, no? V and U. Not B and me. Okay? Yan. What about independent?
X.
X and Z.
X and Z.
Yeah. X and Z. Not Z. X and Z. It's not Z. In British, Z, or something like that. Not Z in British, Z, something like that. Okay. Any question with this, guys? No more? Okay. So another classification, we have classification by order. So meaning, we can talk of first order, second order, third order, degree, first order, second order, third order differential equations. Okay? So again, classification by order. So what is an order of a differential equation, guys? Order of a differential equation. Anyone? Guys? Guys?
Yung highest order derivative of equation.
It is the order of what? The order
Highest
of
derivative.
the highest derivative present, no? The order of the highest ordered derivative, or just the highest derivative if you want. Ordered derivative, ordered derivative. Understood that it is the highest derivative. Highest ordered derivative that appears or present, no? That appears in the equation. Okay? Is my writing clear? Can you clearly see it?
Yes po, it's
Even
very
it's
clear.
small.
Yes, sir.
Okay. What do you see on your screen? Is it the whole screen? No other thing?
Yes po, the
Okay,
whole
good.
screen.
Buong screen
Okay.
po.
So again, the order of the highest order derivative that appears in the equation, that is what we mean by order of a differential equation. So we can talk of first derivative, first DE, second order DE, third order DE, fifth order DE, and so on. Or in general, nth order. Okay? Yan. So again, we can talk of, so here we can talk of first order DE, second order DE. In general, you have nth order DE. Okay, guys? Yan. And how will we know that the order of the differential equation? By looking at the highest derivative present in the equation. So let us have the following examples. We have 3, number 1, 3 x y double prime minus 2 y prime raised to 5, and then plus 3y equals 2x cubed. Okay? What can you say about this DE? What is the order, guys? Guys, what is this?
Second order po.
Second order, no? Second, you can have it in words or in the symbol. Second order. In particular, what differential equation? ODE. Am I correct, guys? Second order ODE. Okay? Because we have already mentioned or discussed the types, no? What about this? Let us have by letter. No? Letter A, letter B. What about the second one? Derivative of C with sub A with respect to P is equal to K C sub AO minus, times E to the negative K, negative K sub 1t, and then minus k sub 2. So this is k sub 1. And then c sub b 1t squared. Okay, guys? So it means c sub b here is constant. C sub a sub 0 is also constant, no? And our derivative is taken saan with respect to t, derivative of what? Of c sub a. Our dependent is c sub a. What about this? What can you say about this differential equation, guys? What is the highest derivative? You have to be careful, ha? You have to distinguish exponent from the order, ha? What's the order of that, guys? Anyone? Guys? Guys? Still alive, guys?
Yes.
What's the order? First order, right? Why is it first order, guys? ODE. Because the derivative involved just first order, okay? What about the second one, the third one? What about this, guys? Guys? Second order. Okay, correct. Okay? Still ODE? No? Letter D. We have x with 3 dots on top, meaning third derivative, minus 5 x with 1 dot is equal to sine t minus x. What about this? Third order, no? Right? Number 5, letter E. What if I have second first partial derivative of beta with respect to big P is equal to negative K partial derivative of beta with respect to big T, then 4 times with respect to big P. Okay? So, take note that if this is fifth order, if you take the sum of the superscript, must be 5 also. Okay? For the letters involved. What about this, guys? This is partial D, no?
Yes.
Am I correct, guys?
Yes.
What is the order?
First.
Huh? Fifth order. Am I correct?
Yes.
Because that's the highest. Okay? Okay, so next. Am I clear with this now, with the order, guys, before I move to the next classification? Guys?
Yes, sir.
Okay, so the next classification we have degree of a differential equation. Degree of a differential equation. Similar to what you had in your algebra. Remember in your algebra, you could talk about first degree equation, second degree, third degree. Remember that? Or nth degree the equation in general. Okay?
Yes.
So we can also talk of that here in DE. And that refers to degree of a differential equation. And when you say degree, we refer to the exponent. Exponent of what? Exponent of the highest order derivative present in the equation. Okay? So again, the exponent, degree of a differential equation, is the exponent to which the highest order derivative is raised, to which the highest order derivative is raised, no? Okay? After the equation, has been written as a polynomial, in all the derivatives involved, no? In all the derivatives involved. Okay, guys? So, in other words, it is the algebraic degree. It is the algebraic degree. Let's emphasize that. Algebraic degree in the derivatives involved. Okay, guys? Am I clear with this?
Yes.
Okay. We look at only relative to what? Once the differential equation is already polynomial in all the derivatives involved, not in the dependent. Because there are two versions actually of the definitions. What we follow normally in engineering is this definition. But there are authors who apply or who use different definition. Polynomial in not just in the derivative, but also in the dependent variable. Okay, guys? Or dependent variables. This is what we're going to adapt. I'm not telling that this is the only correct or this is the only way or the best to adapt, no? But this is what I adapt, no? What I use. But let's say you will be another teacher and he wants to use the other definition, it's all right. So, okay? Because we cannot tell that this author is wrong and then the other author is correct and so on. Am I clear with this, guys? Guys? Okay?
Yes po.
So, number 1, examples. So, number 1, for letter A, we have y prime is equal to x squared times cosine of x minus y. O, check. Look at the derivative. We look at the derivative only, derivative, because that's what we use in the definition. Is it already polynomial? When you say polynomial, what should be the exponent of the derivative? The exponent of its derivative involved must be what? Positive integer. We're not going to consider zero in algebra. Zero exponent is considered also as what? As a valid exponent, no? But here, if you have exponent for the derivative, it will become a constant and not any more derivative. So for the degree, the lowest is first, okay? Guys, we don't have degree 0. Is that clear, children? We just
Yes
have
po.
degree 1. Oh, what is the highest exponent of this first derivative?
1.
1. So we say that this is what?
First degree.
So that is a first degree equation, no? So this is yan, first degree yan, ODE, right? Letter
Yes.
B, What about if I have y triple prime raised to, let's say, 4, and then minus 4 y double prime, and then plus 5 y prime quantity to the 6 plus y is equal to 0. What about this, guys? What can you say about this? What's the degree?
3.
The degree is y3. Remember, how did we define degree? The exponent to which the highest ordered derivative is raised. Once
6, sir.
all that the derivatives involved are written in polynomial forms. Okay? What is the highest derivative, guys?
6.
3. Okay? What is the highest derivative?
3.
3. What is the exponent?
4.
6.
So what's the
Raised to
degree?
4.
Guys, so what's the degree?
12.
Sorry?
12.
Why
No.
12?
8, sir. 8.
Why 8?
Wait lang.
4, sir.
4, sir.
4. It is the exponent of the highest derivative involved. If there, let's say there are 2 third derivatives, you look at the higher one. Okay? Let's say there is still another third derivative. The exponent is 7. It is 7th degree. What's the degree again, children? Guys?
3.
What's the degree again? So the degree is what? 4. Okay?
4.
Fourth degree. Fourth degree ODE. You look at the highest derivative, and then after that, what's the exponent? So 4. So not
Wait,
6,
sir.
because y prime is not the highest. Am I clear with that?
Wait, sir. Pwede pa po ulit.
So let's say I have this one. By the way, if I have a number enclosed, I don't mean an exponent. If let's say I have y and there is a number enclosed in parentheses, 5, what does it mean? In DE, we mean it what? Guys? Order.
Fifth
Okay, guys? It means order, huh? Am I clear with this? Guys? Yeah. So here, that is order. So fifth derivative raised to 4, and then minus 4x y triple prime. Then we now we have plus 4 minus x to the 4th multiplied by y prime plus 3y equals cosine x. What about this? What is the highest order derivative? Or what is the highest derivative?
5.
5.
So 5, no? And what is the exponent of that?
4.
So it is also 4th order, okay? Fourth degree. 4th degree. And what is the order? 5th order. 4th degree ODE. If you're going to, let's say, classify this DE, including the order, so this is 5th order, 4th degree, ordinary DE. Guys, okay, guys?
Yes po.
What about this one? And that is plus kx equals 0. What's the order? Guys, what's the order? What's the order? 2. What's the degree? Meaning, what's the exponent?
1.
1. Okay? So, it means first order, no? I mean, first degree. Second order, first degree, ODE. Okay? So, first degree, second order, first degree. See? It's easy. Now, I would like what I tell you, like what I told you before, the first part of this is boring, no? But once we are done with these basic concepts, it's now like calculus, okay? And then you will say it's better go back to the boring part. Okay, guys? What about this? For partial derivative of f, 4 times with respect to x raised to 2, and that is equal to 2xy multiplied by third partial derivative of f with respect to y, then twice with respect to x. Okay? Then raised to 3. What about this? What is the highest order?
4.
What's
4.
the exponent?
2.
2.
So what's the degree?
Second degree.
Second.
Second degree. You don't multiply, ha? Just the exponent of this highest derivative. Second degree. Okay? Second degree. What DE is this?
Partial.
PDE or partial DE, no? Okay? I think many of you are good in math, no? Because you are responding. Unlike my DE in other school. Okay, now with this, guys, let us have some more. The next examples, something different, no? Because it needs sometimes manipulation, or it needs what? An analysis, no? Meaning you have to be careful, no? So let's have derivative of y with respect to x is equal to square root of x minus y. Okay? What about this? What is the degree? Do you have to rationalize? Because it involves the radical. But the radical does not contain derivative, right? So it means we don't need, no? Okay? Am I correct, guys? It is already okay for the derivative. The exponent is already integer. Am I correct, guys? Guys.
Yes.
So what's the degree?
1.
1, no? This is first degree. ODE. What about if I have a times the partial derivative of u with respect to x, and that is equal to cube root of second partial derivative of u with respect to y, and twice with respect to y. What about this? Can we get the degree immediately, guys? Guys? No, no. We need to rationalize this first, no? Meaning we have to get rid of this cube root first, because this is not yet polynomial in this second derivative on the right side. Guys, clear that? Clear with that? Okay, so what is the smallest number that can make this free of radical? What is that smallest number that we can make as exponent for each side so that the radical will disappear? We have to raise to what?
3.
To 3, no?
3.
So this becomes a cubed, and then partial derivative of u with respect to x, quantity cubed, and that is equal to second partial derivative of u with respect to y. Okay? Can we now determine the degree?
Yes.
What's the highest derivative?
Second.
And what's the exponent?
First degree.
What is the exponent?
1.
1. So it means like this, raised to 1. Okay? So it is what? First degree. Okay now, guys? First degree, PDE. Okay? H. We are now on H. What about if I have 1 plus y double prime raised to 3 halves? And this is equal to 2xy prime raised to 4. What about this, guys? Now, is there any radical contained in a non-integer? Guys, is there a derivative here that is under or inside expression with what? With fractional exponent, not an integer?
Yes.
There is no. So it means we are not allowed yet to what? To get the degree. Okay? So let's rationalize this first, meaning get rid of this fractional exponent. What is that smallest number that will make it integer, guys? Positive integer.
2/3.
We have to raise to what?
2/3.
You have to raise to 2. To 2 only. Because if you raise that to 2/3, so you will have a fraction here for the derivative. You just raise to 2, okay? So raise to what? Raise to 2. No? Not raise our flag. It's raised to 2. Okay? So if you raise this to 2, we get what? 1 plus y double prime quantity cube. Am I correct? On the right side, what will happen on the right side? Guys, 4x squared y prime raised to 8. Okay now? What's now the degree here? If you're going to expand this, what do you think will be the highest derivative? I mean, the exponent of the higher derivative here. Ang higher derivative here yung y double prime because this is just y prime, no? What's the exponent of that?
3.
3, no? So this is third degree. Clear now, guys? Okay?
Yes.
What about if you have this DE? Let's say 4x over 1 minus y triple prime, and that is equal to 2 plus y triple prime minus 3y prime raised quantity to the second. So what about this? Is this already polynomial form involving the derivative or relative to the derivative, the left side? Guys, is this already in polynomial form relative to the derivative?
No.
No, because the derivative is what? In the denominator. What if the derivative is in the numerator, not in the denominator? Is it already okay? Guys? Yes, no? But since the derivative is in the denominator, it's not okay, no? It's not okay to not to be okay. Okay? So let's see. So let's now multiply what? Multiply by what? What are we going to multiply? Multiply by what, guys? 1 minus y triple prime. What happens to the left side? 4x. What about the right side? Guys, 1 minus y triple prime and 2 plus y triple prime minus 3y prime quantity squared. Okay, so this is now product, no? Remember, if you have, let's say, in algebra, x plus 1 multiplied by x squared minus 3, what do you think the highest exponent of x once you expand? Guys. Guys.
X cube.
X cube.
So the highest exponent is 3, no? This will give you what? X cubed, dot, dot, dot. Okay? So it means the degree of this polynomial is 3. Oh, what about here? If I'm going to multiply this binomial in form, this binomial in this third derivative, and this binomial, so this trinomial, I mean, quantity squared, this trinomial quantity squared, what will happen? What will be the exponent of the highest derivative? What is the higher derivative here? The first or the third? The third, no? What will be the exponent once you expand? What do you think,
3.
guys? 3, no? So what's the degree?
Third degree.
So this will be what? It will involve negative y triple prime, no? Quantity, yan. Quantity cube, dot, dot, dot. Okay, guys? Yan, dot, dot, dot. Ay, sorry. Dot, dot, dot. Just 3. Dot, dot, dot. So therefore, this is what? Third degree, no? Yan, third degree. Okay? So, taking or giving the degree is a bit tricky, no? It's not that easy compared with what? Compared with getting the order, okay? By order, you just look at the highest derivative. But here, in determining the degree, you have to get first the highest derivative and then look at the highest exponent of that highest derivative. Okay? What about this? Number ij. Sin y prime is equal to y double prime plus x. Okay? Now, what can we say about y prime here inside y? Is it polynomial in y prime, guys? Is the left side polynomial in y prime? Guys, you're already sleeping. Guys, sorry? Is it already polynomial in y prime? This left side?
Yes, sir.
Yes.
It's no, because it involves trigonometric function. Remember, if I have x plus sine x, it's no longer polynomial. It is actually transcendental na. What in particular? Trigonometric function, because it involves now trigonometric. Okay? Although it has an isolated x. Is that clear, guys? So not anymore. If I'm going to remove sign here, meaning if I'm going to express y prime in terms of this other thing, what will happen? If I'm going to remove, let's say, y prime, I mean sign here, so express y prime, solving y prime, I will get what? Guys, I will get something like this. Y as inverse sine, what? Y double prime plus x. Just one possible case to. One case. Okay? Because if I'm going to add a multiple of what? Anong ina-add dito? Pag nag-add tayo ng a multiple of n pi, 2n pi, yeah, you will have another possible what? Form for this, no? Okay? Yan. Because if you consider this, let's say, an angle or an argument in radian measure, so there are so many possibilities. Kasi if you have just this notation, it means only that what? Guys, if you have let's say just this, it will just be one particular function, no? So your angle is just one possible. So which is in the what quadrant? In quadrant 4 and in quadrant 3. But possible here that y prime has a value that is in the second quadrant or third quadrant. So you really have to add 2n pi, no? Okay? And then And so to have to generate other possibility. So this is just one case, one case, okay? One case. So now, notice that after solving for y prime, this is still transcendental of this, inverse of this, no? So it's not yet polynomial because it involves, again, derivative. Hence, we say that there is no degree, okay? So again, since this cannot be what? This cannot be written free from what? Free from transcendental function of derivative, free from transcendental that's my Saint Bernard. He barks too loudly. So what's the degree, guys? So we say that this has no degree. No degree. Possible for the differential equation not to have a degree. You don't say 0 degree, huh? So, meaning you cannot define the degree, no? No degree. Am I clear with this?
Yes po.
Not 0, huh? Take note. Not 0 degree. Okay? We don't have 0 degree. Not 0 degree. Okay? Yan. Just no degree. Okay now, guys? Am I clear with this now, guys?
Yes po.
Okay. So, what about if I have this? No? Last one, jk e to the xy prime or double y double prime e to the xy double prime equals sine of x plus y plus 1. Okay? What about these children of the Philippines? What about these guys? This is a transcendental, no? What transcendental? Exponential. So there is a derivative in this exponential function. Am I correct, guys? Which is the exponent of e, part of that, no? Part of that exponent. So can I make this without e, guys? Can I make it free of e? I can take what? I can take the ln, right?
Yeah.
If I take the ln of each side, what will happen? I will get xy double prime equals ln of sine x. Am I correct, children? Sine x plus 1. Guys? Now,
Yeah.
do we still have transcendental of the derivative? Does the right side contain derivative?
No.
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 What is the highest exponent for y double prime?
1.
So it is first degree. Okay, guys? So, ODE. Now, again, our definition is based on what I presented to you. There are other books or authors who use other version of definition. Huh? So, to them, so to those with other definition, so there is other rule for that, which I'm not going to discuss that with you anymore, that other rule, because you might be confused. Okay? So, am I clear with that, guys?
Yes po.
So next we have what we call linearity. Another classification of differential equation by linearity. Okay? So linearity of a differential equation. So remember in your in your algebra, so you talk of linear and nonlinear. Remember that, guys?
Yes po.
Now, when you talk of linearity or let's say linear, nonlinear, we refer to what, guys? How do we determine linearity? Based on what? We base it on what, guys?
Polynomial.
We base it on exponent to determine whether it is linear or nonlinear. Let's say I have x squared plus 3. Is it linear or nonlinear? Let's say you have this equation. Is it nonlinear equation or nonlinear?
Linear, sir. Linear.
It is nonlinear. Actually, it
Okay,
is
okay, sir.
what?
Ay, x
It
squared.
is a
Ay,
quadratic equation.
x squared.
Get it, guys? Am I correct, guys? If I have 2x plus 3, is it linear? Equals 0. Is it linear equation? Yes, no?
Yes.
Okay? Now, similar to that, we can talk also of linear DE, nonlinear DE. And when you talk of linear DE, nonlinear DE, we have to check the what? The degree. Automatic, if a differential equation is not first degree, let's say you have a differential equation that has no degree. So no degree, second degree, third degree, fourth degree, automatic they are what? Nonlinear. Clear, guys? But it doesn't mean that if it is first degree, it is already linear. There are also first degree that are not linear. But to determine linearity, to be linear, so it must be first degree. But again, not all first degree differential equations are linear, but those that are candidates for linearity in linear are those that are first degree. Okay, guys? So let's see what we can say about linearity of a differential equation. A differential equation is said to be linear if all of the following, or it's written if all, not just one. Okay? So if it's all, okay? If all of the following I think to Vilma Santos, 8, at least 8, no? Remember Vilma Santos advertisement? If all of the following are what? Satisfied, all of the following conditions are satisfied. Number 1. So the first condition, guys, any dependent variable, any dependent variable and its derivative and its corresponding derivative, yeah, and its derivative can be written with degree 1. You can express with degree 1. Can be written with degree 1. You can express it with degree 1, both the dependent and its derivative. Is that clear, guys? Meaning the exponent of both must be what? 1. You can express. Is that clear, guys? Second condition. So there are 3 conditions. Second condition, no product of dependent variable and or, what does it mean? Dependent, dependent derivative, dependent, and or any derivative, must occur. Okay, guys? So meaning, no product of dependent on any side of the equation. So no product of dependent derivative or derivative. Is that clear, guys? The third one, free from the transcendental function of a dependent variable. Free from transcendental function, meaning no transcendental function. Transcendental function of what? When you say transcendental function, trigonometric, inverse trigonometric, exponential, logarithmic, hyperbolic, inverse hyperbolic of what? So free from transcendental function of what? Of a dependent variable and its derivative. No transcendental function. So be careful ha, in our degree definition, we consider only the derivative. But for the dependent, linearity, we consider both the dependent variable and its derivative. No transcendental function of dependent and its derivative. Okay? Is that clear, guys? Guys?
Yes po.
So we have here no transcendental functions of a dependent variable and its derivative. So these three conditions. Once these three conditions are satisfied, then we say that the given DE is linear. So otherwise, so there is otherwise. Yan. Yan. Otherwise, it is nonlinear. Otherwise, the D is what? The D is non-linear. Is that clear, guys? Non-linear. A question here, guys.
None naman po.
Okay, so let's have the following examples. So this will be the last for our discussion for today. And then I will be sending to you, what you call this? Pre-recordings. And then you're going to watch that during your asynchronous on Monday. Okay? So that by next meeting again, then once we meet, you can ask me of anything that you did not understand, for instance, or you want understand during our synchronous. And then we will be continuing. Okay? Okay, number one. Let's say I have x cubed minus 1 multiplied by y double prime minus 3x y prime plus 7 y equals x to the fourth cosine x. Oh, is this linear or non-linear, guys? Oh, check the derivative. What's the exponent? 1. So it is positive integer. Y prime, okay. Y, okay. So the dependent. So it means it is what? Linear. All their exponents are what? 1. Is there a product of derivative and y? No. Is there any exponent other than 1 for the dependent and derivatives? No. Therefore, this is what? Linear. What DE? ODE. In particular, this is linear in y. Okay, guys? Guys, linear
Yes.
ODE in what? In Y. In what variable? In Y. Okay? Letter B. If I have, let's say, fifth derivative of Y with respect to X. Yan. And then, plus 4 times fourth derivative of Y with respect to X. Minus 5 third derivative of Y with respect to X. Minus 2Y equals 0. What about this? Guys, is it linear? Linear, no? Linear ODE in what? Still in Y, right? Okay? Yeah. Letter C. T to the fourth. Then, by the way, in case you want to leave now, you go and go ahead. I will continue for recording purposes. Okay, guys? So, just to
Yes,
complete
po.
the lecture for today. You can go ahead if you want. Even if it's already time, you can go ahead. T to the fourth, they multiply to the third derivative of X with respect to T, and then minus cosine T, second derivative of X with respect to T, and then plus 4T cube X is equal to negative T to the 3 halves. So this one, look at the dependent X, independent T. So we don't look at the independent, we just look at the independent and derivative. I mean dependent and derivative. So derivative, so okay. So okay here, linear. What about the X? Is it linear? Yes. Okay. So this is linear DE. Linear DE in what variable? Linear ODE in X. Okay, guys? Guys.
Yes, sir.
Yes po.
Okay, letter D. If I have fourth derivative of W with respect to, let's say, theta, and this is equal to theta multiplied by W minus theta. Oh, what about this? Is this linear? Yes, no? Linear. Because if I multiply this, W is multiplied not to dependent. It is multiplied to independent. Okay? So linear in W, no? Linear ODE in W. Okay, guys? Yan. What about if I have letter E? We have X, Y double prime. Sorry. Y double prime minus 2x, Y triple prime is equal to 4x cubed. What about this, guys? Is this linear or non-linear? Guys,
Mm.
None, sir.
non-linear. For what reason?
Dahil po ba naka-cube yung 4x?
What is the reason, guys? Because of this. Okay? This is product. Product. Involving what? Involving both dependent and independent. I mean, both dependent and derivative. Okay? Dependent and derivative. So, violation. Non-linear in what? So, this is non-linear ODE in Y, no? Yan. Non-linear ODE in what? In Y. Because of this. F. What about if I have derivative of W with respect to T minus second derivative of W with respect to T is equal to what? Cosine 2W. Is this linear or non-linear, guys?
Linear.
Non-linear. Why non-linear, guys? Non-linear in W. Why non-linear? Because of this. There is a transcendental of what? In particular, cosine of dependent variable W. W is dependent. If it is T, so it is linear, but this is W inside cosine. So non-linear. Okay? Guys? Guys? So what about if I have y double prime quantity cube equals xy prime? I mean, because xy. Oh. So why is it non-linear, guys? This is also non-linear. Why non-linear?
Exponent, sir.
Because of what? Exponent of what? Because of this, no? The exponent is what? Is 3. Okay, guys? H. We have second partial derivative of u with respect to, you can go ahead, guys, if you want. If no replying, I assume that everybody has left. Second partial derivative of u with respect to x is equal to 2 times first partial derivative of u with respect to y. So this is linear. Linear ODE. Because PDE, sorry. Linear PDE. Because this involves what? Two derivatives that are what? That satisfy the three conditions na. Okay. What if I have W, second partial derivative of W, of V with respect to X, and that is equal to second partial derivative of W with respect to Y is equal to first partial of V with respect to Y, then minus first partial derivative of W with respect to X. What about this one? This is non-linear. Why non-linear, guys? Guys, why non-linear? Guys, non-linear PDE because of what? B and W are both dependent, and W dependent multiply to a derivative. Guys, na? Dependent times derivative. Okay, guys? Is this clear now, children? Okay,
Yes,
so that's it. If you don't have any more questions, okay, you can now leave, guys.